Good morning, friends. How are you? All are fine? Okay. So, we were discussing the design of a stator. Now, we will proceed further in our topic. So, the first topic is conductor area. Now, stator conductor cross section AS. Cross section area AS equals to IS upon delta S, that will be equals to IPH upon delta S. Stator current per phase output power Q equals to 3 VPH into IPH cos theta into eta into 10 to the minus 3. So we can find the IPH from this equation, that will be equals to Q into 10 to the power 3 upon 3 into VPH cos theta into eta. And delta S is current density in the stator. So now the choice of current density, please keep noting, we will go very fast. So now choice of current density, advantage of high value of delta S. What is the advantage of high value of current density? The conductor cross section will reduce and the reduce conductor cost and weight. So the two advantages of high value of delta S, current density in the stator. Conductor cross section will get reduced and conductor cost and weight will also get reduced. Disadvantage of high value of delta S, resistance will increase. Number one is resistance will increase. The copper loss will also get increase. And temperature rise will also increase, and with increase of all the things efficiency will get decrease. So once again I am repeating, the choice of current density is advantage of high value of delta S, conductor cross section reduced and reduced conductor cost and weight. Disadvantage of high value of delta S, resistance increases, copper loss increases, temperature rise will increase and efficiency will finally reduce. Usual range 3 to 5 ampere per mm square and higher for smaller machines. Now we will come to the next topic, shape and size of the stator conductor. Shape and size of the stator conductor. So it can be rectangular, it can be circular. AS less than 5 mm square for the circular conductors. AS will be greater than 5 mm square for rectangular conductors. For rectangular conductors, width to thickness ratio must be between 2.5 to 3.5. Standard bare size of round and rectangular conductors from standard tablets. Once again I am repeating, what will be the shape and size of the stator conductors? AS less than 5 mm square for circular conductor. AS will be greater than 5 mm square for rectangular conductors. For rectangular conductors, width to thickness ratio must be between 2.5 to 3.5. Standard bare size of round and rectangular conductor from standard tables. Now slot area, area of a stator slot. Slot area is occupied by the conductors and the insulation. The slot area will be occupied by the conductors and the insulation. Around 25 to 40% of slot area is used by conductors, remaining by insulation. So we can have a formula AS equals to ZS into AS by KS. Please keep noting, I will be going very fast. AS equals to JS into AS by KS. ZS will be conductors per slot, KS will be slot space factor. So we can write KS equals to copper area by total slot area, that should come in between 0.25 to 0.4. HV machines have lower KS due to more insulation. Once again I am repeating, slot area is occupied by the conductors and the insulation. Around 25% to 40% of slot area is used by conductors, remaining by insulation. AS equals to ZS into AS by KS. ZS conductors per slot, KS slot space factor, copper area by total slot area. Please keep noting 0.25 to 0.4 HV machine. I have lower KS due to more insulation. Area of a stator slot. So this you can find is lip. This one is the lip, and below that wedge is there. Then the conductor insulation is there. Then slot liner is there. Below that slot liner is there, and in between that coil separator is there, and after that coil insulation, and then conductors. So once again I am repeating, first of all lip is there, then wedge, then conductor insulation, then slot liner, then coil separator, then coil insulation, and then conductors. So area of a stator slot, slot liner, that must be 0.5 to 0.7 mm. Coil separator length is 0.5 to 0.7 mm LV, 0.8 to 1.2 mm for HV, wedge 3.5 to 5 mm, and lip will be 1.0 to 2.0 mm. Now width of the slot and tooth at air gap must be nearly the same. Width of slot and tooth at air gap must be nearly same. If slot is too wide, then tooth is very thin. So tooth will be mechanically weak. If the slot is too wide, then tooth is very thin. Tooth will be mechanically weak. Tooth flux density will be too high, and limit of tooth flux density is 1.6 to 1.8 Tesla. Slot should not be too deep, because it will increase leakage reactance will increase due to this. Slot should not be too deep, so but otherwise it will increase the leakage reactance. So the guideline says that ratio of slot depth to slot width should be 3 to 5. So this one is the stator core which you are looking, this one is stator core, then tooth, and this is the slot, and this one is the air gap, and now this is the rotor. So please write the question. Determine the main dimension, turn per phase, number of stator slots, conductor cross section and slot dimension for a 250 HP 3 phase 50 Hz 400 volt 1410 rpm slip ring induction motor. Assume BAV equals to 0.5 Weber per meter square, AC 30,000 ampere, conductor per meter, efficiency 90%, power factor equals to 0.9, winding factor equals to 0.955, and the current density equals to 3.5 ampere per mm square. The slot space factor is 0.4 and the ratio of core length to pole pitch is 1.2. Assume delta connection. So the machine runs at 10 rpm, thus synchronous speed corresponding to 50 Hz, and 4 pole is ns equals to 1500 rpm, and we know small ns equals to ns by 60. So 1500 by 60 will become 25 rps. C naught equals to 11 BAV AC KW eta cos theta into 10 to the minus 3. So now you can calculate the value of C naught, 11 into 0.5 into 30,000 into 0.955 into 0.9 into 0.9 into 10 to the minus 3. So please keep noting, I'll go very fast. Please keep noting. Once again I am repeating. C naught equals to 11 into BAV AC KW eta cos theta into 10 to the minus 3. So we will keep the value of all those parameters in this equation. So 11, so the equation will become 11 into 0.5 into 30,000 into 0.955 into 0.9 into 0.9 into 10 to the minus 3 equals to 127 into 63. Q equals to C naught D square LNS. So from here we can calculate D square L by putting the values of C naught and balance parameters in this equation, and we will get D square L equals to 58.4.5 into 10 to the minus 3. So given L by tau equals to 1 by 1.2, and we know the formula L by tau equals to LP by pi d, that is equals to 1.2. So L by D equals to 0.942. Solving for L and D, we will get L equals to 0.375 m and D equals to 0.395 m meter. So D equals to 0.375 0.395 meter and L equals to 0.375 meter. After each 10 centimeter length we need one duct, as we had discussed earlier. Since L equals to 37.5 centimeter, there will be 3 duct in the stator. Thickness of duct, that will be equals to 10 mm. Taking stacking factor 0.9, net iron length Li equals to 0.9 into 0.375 minus 3 into 0.01, that will be equals to 0.3105 meter. Now the turn per phase, that is flux per pole phi equals to BAV Li into tau, pole pitch tau pi d by p, pi into 0.395 by 4, so that will be equals to 0.31. So phi will be equals to, we will put the value in this equation, so phi will become 0.5 into 0.3105 into 0.31, that will be equals to 48.13 into 10 to the minus 3 Weber. Since the machine is delta connected, so Vs equals to EPS, that is equal to 400 volt. Now TPH equals to EPH by 4.44 F into phi into kW. TPH equals to EPH by 4.44 F into phi kW equals to 400 by 4.44 into 50 into 48.13 into 10 to the minus 3 into 0.955. Please calculate the value. Okay, so the now value will come 40. So now the total conductors will be Z equals to 3 into 2 into TPH, that will be equals to 6 TPH. So 6 into 40, that will equals to 240. So total conductors equals to 6 times the turn per phase, that will be 6 into 40. So these conductors need to be distributed among the slots. These conductors need to be distributed among the slots. Number of a stator slot SG. The guideline is slot pitch to be between 15 to 25 mm. The guideline is slot pitch to be between 15 to 25 mm. Thus, number of slots should be lie between this value. So SG equals to pi d by 25. We will put the value of d in this equation. So pi into 0.395 into 10 to the power 3 divided by 25, and we will get the value that will be approximately equals to 50. 2 Sg equals to pi d by 15, pi into 0.395 into 10 to the power 3 by 25, that will be approximately 84. So Sg will be 50 to 84 and Z will be 240. Number of slots per pole per phase, Qs should be multiple of 3 for integral slot winding. So Qs 3 and Sg will be 3 into 4 into 3, that will be 36. And when Qs equals to 6, to 6 into 4 into 3, that will be 72. But we cannot distribute the total 240 number of conductors in the 72 slots. So we have to go for fractional slot winding. So in this way you can decide whether you have to go for integral slot winding or fractional slot winding. Number of stator slots Sg equals to 50 to 84 and Z is 240. Let us check with number of slots per pole per phase. Qs equals to 2, 4, 5. Use fractional slot winding. So Qs 2, then it will Sg will become 2 into 4 into 3, that will be 24. And when Qs equals to 4, then the Sg will become 4 into 4 into 3, that will be equals to 48. And when we will put the value of Qs 5, it will become 5 into 4 into 3, that will be 60. Thus finally we can choose Sg equals to 60 slot with 4 conductor placed per slots, so that total 240 conductors are accommodated. Now stator conductor cross section AS, cross sectional area AS, IS by delta S equals to IPH by delta S. Stator current per phase. Output power equals to Q 3 VPH into IPH cos theta into eta into 10 to the power minus 3. So this output power Q equals to 3 VPH IPH cos theta into eta into the power 10 to the minus 3. So we can calculate IPH, that will be equals to Q into 10 to the power 3 upon 3 VPH cos theta into eta. So we will put the value of this parameter in this equation. 250 into 0.746 into 10 to the power 3, 3 into 400 into 0.9 into 0.9, that will be equals to 192 ampere. Please keep writing, I'll go very fast. Given current density in stator delta is 3.5 ampere per mm square, so AS will be coming 192 by 3.5, 54 that will be 54.86 mm. So here we need to check the nearest conductor dimension from the standard chart. So now area of stator slot AS, slot area is occupied by the conductors and the insulation. Once again I am repeating, slot area is occupied by the conductors and the insulation. AS equals to ZS into AS by KS. So AS will be equals to 4 into 54.86 by 0.4, that will be equals to 548.6 mm square. AS will be conductor area, that is 54.86 mm square. ZS will be conductor per slots, that is 4. KS will be slot space factor 0.4. Now guideline says ratio of slot depth to slot width should be 3 to 5. Width of the slot and tooth at air gap must be nearly same. So AS equals to HS into WS equals to 548.6 mm square. So HS by WS equals to 3. Now HS equals to 40.6 mm and WS equals to 13.5 mm. So WT and WS are very much different. So we can choose a different ratio of slot height and width. We can have a formula W2 equals to tau Sg minus Ws, Wt equals to pi d by Sg minus Ws, and we can calculate the Wt, that will be equals to pi into 0.395 into 10 to the 3 by 60 minus 13.5, and we will get that value 7.18. Now the flux density at a stator tooth. Once the stator slot dimensions are fixed, the average flux density in stator tooth can now be determined. So once again I am repeating, once the stator slot dimensions are fixed, the average flux density in the stator tooth can now be determined. Maximum flux density in the stator tooth should be not exceed 1.7 to 1.8 Tesla. Otherwise iron losses and magnetizing current become too high. What will be the impact of increase of flux density beyond 1.7 to 1.8 Tesla? The iron loss and magnetizing current become too high. If the limit is exceeded, stator slot and tooth dimension need to be adjusted. So flux density in stator tooth, maximum flux density in stator tooth should be not exceeding 1.7 to 1.8 Tesla. Maximum flux density occurs at, please keep noting, maximum flux density occurs at root of tooth nearest to the air gap. Maximum flux density occurs at root of the tooth nearest to the air gap where the tooth width is minimum. So you can see here, this is the stator core and this is the tooth. This is the stator core and this is the tooth. And here this is the HS and this is the WT. You can easily find this is the air gap between stator and rotor. This is the air gap between stator and rotor. This is the slot. This is the slot. This is the width of the slot and this is the height of the slot. And the tooth is this. So flux density at a stator tooth, that is B tooth equals to BT equals to flux per pole by area of a stator teeth per pole at air gap. So you can calculate that BT equals to phi by ATP, that will become BT equals to phi by Sg by P into W2 into Li. So you can here easily locate this tooth area and this one is the ventilation duct. So the equation is BT equals to phi by Sg by P into W2 by into Li. Now we will put the value of these parameters in this equation and it will become 48.13 into 10 to the minus 3 divided by 60 by 4 into 7.18 into 10 to the minus 3 into 0.3105, that will be equals to 1.43 Weber per meter square. This is within maximum limit of 1.7 to 1.8 Tesla. So this is within the maximum limit of 1.7 to 8 Tesla. Thus we can confirm that design is okay. So we can confirm that design is okay. So everybody listen and please keep noting. Now depth of the stator core. What will be the depth of the stator core? As I had discussed earlier that this is the stator core, this is the tooth, this is the height of the tooth, and this one is the air gap. So DCS, depth of the stator core. Now this is the DS, this is the DCS, this is the stator core. ACS is net cross sectional area of the stator core. ACS will be the net cross sectional area of the stator core. DCS equals to depth of the stator core. Flux distribution in the stator core. This is the stator core, this is the stator core, this is the D naught, this total height will be the D naught, and this is the phi C, that will be equals to phi by 2. Total flux get divided in half. Total flux will get divided in half when passing through the stator core. When that flux is passing through the stator core, then the flux will get divided into two parts. So phi C equals to phi by 2. To restrict the power loss and magnetizing current, the flux density in the stator core must be within the range of 1.2 to 1.5 Weber per meter square. So BCS must be in between the range of 1.2 to 1.5 Weber per meter square, because we have to restrict the power loss and magnetizing current. So ACS equals to phi C by BCS equals to phi C equals to phi by 2, and BCS, so ACS is equals to DCS into Li. So you can easily calculate ACS equals to DCS into Li. Li is the stacking factor, Li equals to stacking factor into L. Now ACS equals to phi by 2 BCS. Please keep writing. Phi equal by 2 BCS and DCS equals to ACS by Li. So DCS equals to phi by 2 BCS into Li. Now OD of the stator, D naught equals to 2 DCS plus 2H plus D. Now OD of the stator, D naught 2 DCS plus 2H plus D. So D naught, this value D naught will be equals to 2 times DCS plus 2HS in plus D. So now you can easily design the stator core for the motor. So now we will move forward and you can solve the problem here which is indicating. Now I think that the design of the stator must be clear to you. If any doubt, please ask. So I know that I have taught you very fast, but you can easily understand all the things. So no question. So now thank you very much. In next class we will start the design of the rotor. We will start the design of the rotor. Thank you so much.